Hello, how are you doing? Okay, we'll start in about a minute. I hope you're doing well. Go ahead and check out your Unit 5. Um, I'll share screen shortly. So look at Canvas. Okay, that. Let me get my notes open real quick. Okay, I'm doing well. Thank you for asking. Um, yeah, let's share screen. All right, so really quick announcement. I think I push a few things out on announcement for Canvas Course Room. One was yesterday. I think I posted the Riverside County. So if you're looking for internship, this is available to you. And we've been working with Riverside County for the apprenticeship program in cybersecurity. But if you look at these jobs, they do have some general ones and also some IT ones, like this one is IT related. And then there are some other areas that you can apply as interns. So if you're looking for work, if you wanted to build some technical experience, it's also good to get into the IT field and get your foot in the door. Many of my IT and security students, they like to start out with some internship to get them some experience. So this is also open to you. I also push out another one. Let me come back to the announcement. Microsoft has released a scholarship. This is mostly focused on the cybersecurity. It's not a huge scholarship, but it looks really good on resume if you're a recipient, and also they provide like resources for you. A lot of the times it's mentor and other things. So you can check this out, get some additional funds to be able to get, whatever you need. And so you can apply for it if you like. Okay. And then I also added an I3 opportunity that's through Moreno Valley College. I work with some of the faculty in I3. I originally was part of it, but I am in other programs now. So if you're interested in that, you can also check out the announcement for I3. Okay, which should be here. And mostly just for innovation. So if you want to design, create something, you can apply for that. Okay. All right. So in this week, we're going to work with data loading a little bit. We're going to talk a little bit about data movement, like load and store, a little bit closer as we have seen these instructions in the past. We're going to do a program in the lab this week that's going to address an equation, and it's going to focus on, days of the weeks and so on. So let's take a look at the notes, and this is the second part of chapter 5. I broke this up into two parts. Last week we talked about the first part of chapter 5, which mostly talks about operational instructions. We built program that work with branching, and we did talk a little bit about data movement. So now when we take a look at this is very important. It plays a very big role in your program. We have to find a way to access data So we normally put a label to an address and be able to load that to the register so we can be able to add some form of values, so we can use the operational instructions with the data movement instructions to really access the data that is stored, or we can retrieve the data that is loaded. So earlier we talked about how when we use the load is really when we want to be able to read the data to the register. Basically, it's a way for us to access the memory location. And your register is really the middle point in how we would be able to temporarily see. So in your simulator, you should not look at your register value frequently, right? Everything that we should use the memory address to be able to really look at our data as it computes. So we're going to see load and store quite a bit, sometime at the beginning of the program, sometime throughout the program. And so far in our labs, we have been using load and store at the beginning and at the end of the program. So we learned that in LC3, we're using LD for direct load, LDR for load to register, LDI for indirect load, LEA for load effective address. So that's pointing to the address, and normally we would use this for string. ST for store direct, STR for store register, and STI for indirect store. And, as I explained before, the load, the LD and the LDI, the main difference is LDI works with memory address pointing to memory address, where LD it goes to the MAR and be able to locate the address um, of what you're trying to load as it's defined in your data section. So when you're looking at the instruction itself for the LD, right, this is defined as a PC relative mode. So I can achieve the same thing using other loads, but in this case, if I'm using LD, it is going to be using the program counter. And with that, we can use any of the register. So if I have a label X, let's say I define that later in my program with the dot fill, I can load it to register 1, and we've seen this. So you can do a direct load. So when you load directly, this is going to be your bits in binary, 0010. The register 1 is going to go here in these 3 bits. That's indicated your destination register. And when you do that, the PC offset, this is going to be the 9 bits. So this is going to store the information for label X. And this is how it's going to know exactly where label X is defined later in the program. So if I have X dot fill, let's say 3150, this is going to be what is tied to the label X. And when you load that, register 1 will be able to access the location in memory, which is hex 3150, that's the address, to be able to get your data. So at the micro level, at the lower level than what we've seen with the instructions, it's going to take the memory address that we use with the dot fill, and it's going to add it to the program counter. And after that, it's going to put it into the MAR, memory address register. Remember that the MAR is used to track all the memory addresses that is either assigned or defined, or would be next in queue, right? Like when we're looking at the program counter, how it's able to see what's the next instruction and so on, and where that's stored. So once the MAR have this information, offset plus PC, it's going to transfer that to the MDR. And now we're entering the area with the data. So for the data side or the destination register, it's going to be able to transfer that to the MDR. So that way it can set certain type of conditions if needed, in the case where if we branch to a label, let's say I want to later on branch positive to the label X, this is where it's going to go and find the information from the register to be able to activate the condition that is set for my branching, which is then ultimately, we saw that last time where it would be either a 0 or a 1 to indicate, right, for the bits that's on and off for the branch. Any question with the LD? Okay, so the LDR, as we mentioned, it is achieving the same purpose. But when you look at it closely, it is a little bit different in how it is at the micro instruction level. And so LDR work with base offset mode. Unlike LD is using PC relative mode. This is program counter, and this is specifically with the base offset, which reference addresses. Okay. So the true difference is that different in the address calculation, it's going to do that. Instead of like LD, it would take offset, which is the address. It's going to add it to the program counter. In the LDR, it's going to take the offset, which is only 6-bit, and it's going to add it with the base. So it's going to, the content of it is going to be the register plus the address. As the instruction is indicated, when you load register, it's going to refer to the content of the register added with the address, which is what you have with the base and the offset. And once it has that, it's going to put it to the MAR, which is your address register, memory address register. And then it's going to load it into the MAR as an offset 9 plus an MAR. So at that point, your offset is going to be loaded to the MAR and then transferred to the MDR. So the true difference between the LD and the LDR is that the calculation before it goes into the memory address register is different. But we can accomplish the same thing, right? As we load to read. So when you look at this before it goes into the MAR, PC offset or PC mode is different than your base mode. And then for the LDI, which is an indirect mode, we saw the diagram last week where you kind of see how we have a memory array. You have one address pointing to another address. So it's accomplishing the load like the other two, but it's loading from a memory address. Okay, whereas when we look at the above, it's gonna load the value into the register from the PC relative mode or the offset mode. So here, the LDR load from register to register basically, and then the LDI is gonna load from memory to memory. And you would use the label to identify the address that you're loading. So I can do LDI R1 label X, right? Just like the others. And so we always want to use a label to be able to load to the register, and that label is tied to an address. Okay, with that, let's answer some questions. And I'm a little verbose in my answer, and you can summarize it, or you can, you can put it verbatim, however you want to do this. So for question 1, it says refer to the notes in the textbook. Describe the primary differences between LD, LDI, LDR, and LEA. So for the LD, we mentioned that it is PC relative mode. It can be loaded to any of the general register 0 through 7. The LD instruction takes the source label and stores its address into the destination register. The source label must be within 255 lines of the LD instruction. So let's say that my code for the load, it's the second line, right? You often see this after the origination address. I normally want to clear, register, and load. So that will be 2002, or 3002. In 3002, what you see is your label define has to be within 255 lines. Last week, I told you that you shouldn't use memory addresses that's too far down because there's limitation in how it can retrieve it. When you pass the 255 lines, it's not going to be able to locate it. So it is best that we want to fill our addresses within 255 lines from the loading instructions. So if I'm at 3002, right, I can fill at 3200, right? I don't want to fill at 3500 because that's too far. Okay, so when I fill hex 3500, it's exceeded the 255 lines after at the loading instruction, it would not be able to pull it. Okay, so when you're using LD, pay attention to the fill address and make sure that it is 255 address within those 255 address at the loading instructions or from the loading instructions. For the LDR, we know that it is base offset mode. It's the same as, it achieves the same purpose as the LD. It's different in address calculation. It takes your base plus your offset, or it can be the content or the register plus the address. Sometimes you have register that already have values. So it would take that, whatever value that you have in that register. Let's say that I have hex A in the register, and it's gonna do the arithmetic with the address. And LDR stores the source register value plus the immediate value offset. So when we say immediate value, you should know that it is either hex or decimal, like how you've seen with, I can load like a hex 3, I can load a D, a hex D, and so on, right? So you can use it and it treats those values as addresses, actually. And it's going to store the values in the destination register, right? So in this case, we're looking at the hex 1, which is an immediate value. It's a number. And we are going to compute it with register 2. So the content of the register 2, whatever is in there, it's going to take this, and this is going to, it's going to do the adding, and it's going to put this, the result in register 1. So if I load register 2 with another label, which is filled with another address, it's going to take that address and it's going to add it with the immediate value, which is hex 1, and then combine, it's going to put the output or the result in register 1. Whereas if we're looking at the load, the LD, it's simply an address for the label 1. Let's say hex 3100. It's going to take that and it's going to add it with the program counter value and add it to register 1. So when you're looking at the content of the register at that line, it's not specifically just the address. It's the address plus either the program counter mode for the LD, and if it's the LDR, it's the content of your source register, or it could be an offset value. Okay. So this is why sometimes students refer to register when they simulate and they look at the value and they ask me, why does it have other values besides the initialized value? It's because you have to look at the the content of your program and where it's at in the program. And it's going to refer to also the PC, the program counter address, right? Your code address, along with whatever you're trying to do here with the load or the store. In the LDI, which is the indirect load, we talked about this before. So the main difference is we're going to load from a memory address. And when we use the label, this is a way that we can pass the address in assembly. Basically, we're taking a memory address and passing it to another memory address. So it treats the source register as an address, and it stores the content of the memory at that address in the destination. So in this case here, we have the label 2, which is tied to an address. And we're going to load it to register 1. We've seen this a lot in our lab, right? Because I prefer to use LDI. So what you have is it's going to take the content of label 2, okay, at the address that we fill, and it's gonna go to the address of label 2, and it's gonna bring that to the address of the register. Okay, so it's tying an address to an address, and that's how it's able to pull the content of the label 2. Any question? For the LEA, which is the immediate mode, it does not access memory. You're going to load an address directly into the register. So when we define a string, let's say that string is fill, right? It's just going to be at that instruction location, and it's going to pull it from the address of the instruction. So when you're looking at your line, right, you have an LEA, let's say string R0 string 1, and down at the bottom, right, you say string 1 dot strings. This is my hello world, whatever. It's gonna it's gonna access the address of where you define that string in your code, and that's how it's able to associate that string with the register 0. Unlike the other, where it's using addresses to be able to associate other addresses, in this case, it's bypassing memory. It's directly going from register to the location of the defined string. Any question? Okay. So we want to understand the difference between these, right? Some of the questions will come up on your quiz and your final relating data movement instructions. Load is very important, and also store is very important in my program. So we try to apply a lot of these concepts throughout our program and eventually your project. So make sure that we see. And it's really, thinking about this is really about how you want to approach the problem when you're trying to solve a problem with your program. What are you trying to achieve? And you have to think about space and how that can play into efficiency, okay, at assembly level. So space is in memory. All right, so now let's go to the store. Okay, so there's more diagram. For the store, we know that this is where we're gonna write data. So if you load at the beginning, if you read data at the beginning, you have to write it at the end. And in some cases in the future lab, you're going to see that we are going to write data at the beginning and we're going to read it at the end. It really depends on the type of program or the problem we're trying to solve. So store is really to write data. And when you're using the ST, just like the LD, it is PC relative mode. And so for the ST, this is the binary. You're going to have 0011. And your source register is always going to follow your opcode. And then after that, it would be some form of label or ultimately address. So if I'm using, let's say, a label called, for example, label 2, like what we said earlier, for that label, whatever the fill address is, it's going to be able to access that location. So on the micro instructions level, and you see this in the textbook along with if you look at the PowerPoint. So it's going to use sign extended from your bit location 8 to 0, which is right here. Okay. So half of it is going to be dedicated to your memory address. And so for these bits, it's going to add the value to increment in the PC, then store it in the MAR, because remember that the program counter is really a way to track, right, what's current and what's next as far as the sub process in our microprocessor. So what you have is it's going to use this address to be able to increment, to move in the program counter. So that's why it can access it. Now, after that, it's going to put that into the MAR, which is used to track addresses, and then put the content from the source register into the MDR. So the MDR is going to allow us to be able to pull data. So these two are always going to work together to be able to transfer content between the addresses and the data. So basically the MAR ultimately at the end is going to point to the data location as it got the content in the MDR. Okay. So an example of store is this, label 1 to register 1, or from register 1 to label 1. So we're going to store the content from the register to the label 1. So our source register is going to put it into the MDR. And then from there, it's going to take the content from MAR, from memory, to associate that with the data, okay, at the memory location. So that's how it writes. For the SDR, this is base offset mode, similar to the LDR. And just like the LDR that we talked about earlier, right, you got bit 6 to 0, that's going to be your offset. And then your base is going to be from 6 to 8 or 8 to 6. So when we're doing a store register 3, right, to your base R or offset 6, what you have is your memory address register is going to load, right, the address here to the base, and then it's going to transfer that into the MAR. This is where it's going to track where that is. So think of this as a way to locate where everything is in memory, the MAR. So we need to bring it into that register so it can find it. And then your source register, in this case, register 3, the content of it, it's going to go into the data side, which is your MDR. And then it's going to take what's in the MDR, use the MIR to find the location, and it's going to point it. So basically, it's going to point to the data from an address. Okay. All right. And then for the STI indirect store, so the content of your source register is stored onto the memory location. It contains the operand address, and that allows it to access full memory address space. So this utilizes the entire address space. Hence, you're going to see that it doesn't require the base. It uses bit 8 to 0 for the entire PC offset, which is PC offset 9. So when I load the label here, I'm storing the source register, right? Register 6 to Z. So in this case, Z address is going to occupy the 9 bits here. Okay. And here it gives you the micro instructions. There are extra steps in STI compared to ST or STR. As you can see, it is address to address. So it needs to load, it needs to transfer the content of the address 1, then transfer that address to the MDR, and then back to MAR, take the content of the address 1, and then move the content of the register into the MDR. So what it's doing is it's transferring all of these things to be able to get to address 2. Because when we first start out with the MAR, which is address 1. Put it into MDR, then take the MDR, go back to MAR, and then take the content of the address 1 and go to the source register, load that into the MDR, and that's how it's able to get to address 2. It's address to address for STI. And for load effective address, it just load the address directly into the register where we fill string. So let's summarize that and answer the question. So for the ST, move content from your source register to memory. That's just a very brief answer for that. And in this case, let's say that I have a label called ADDR2, and I'm going to store to that location from register 1. So here what we're doing it stores a value, right, from the source label to address 2 or ADDR2 into the destination register. For the STR base offset mode, it's going to store the value into the base register from the offset, which is, it could be an immediate value like a hex or a decimal. In this case, I'm using a decimal 1. So we can do it like this. Sorry, that's confusing because we can store from a register to a register, or we can do an STR R0 with a decimal 1, which is an immediate value. So your operands it could be a register, or it could be a value, a numerical value, an immediate value. So what it's going to do in this case, in the first example, it's going to store the value in the source register. It's going to take that and then it's going to bring that into the destination register. And if you're using an immediate offset, it's going to compute that with whatever the content that's in the destination register. Okay. For the STI indirect mode, the content of the source register is stored onto the memory location. And it's going to use that address to be able to access another address. So it accesses the full memory address space. Because it started out with 8 bits for the offset. And then when it finished, it's going to access the entire address space, which is 16 bits. Address 1 is 8 bits and address 2 is another 8 bits. So combined, you have a full address space, which is one word. So when you're using this, any immediate value, like a label or an address or a hex value, it's going to treat it like a memory address. And it stores that value as addresses into the destination register. So if I use a store with a value here, it's going to associate that. It's going to treat it like an address. If I use a label, it's the address of the label, right? Any question? Okay. So as we proceed after the store, okay, and you can check out your notes, you can summarize it or you can put it verbatim, that's up to you. We worked a little bit on branch, but today I'm going to emphasize a little bit on jump. And so in LC-3 in this class, we're going to use JMP for jump. This is also equivalent to your unconditional branch. So what that does is we can send it to another section of our code using jump. So I can do some operation with my instruction, and then I would tell it to jump to a later part of my program. So that way it would execute there, and then I can move it back and forth. So it's a way that we can control how the flow of our program would be. We can force it to go to that section of our code and then do something there. So how does it really do it? When you specify a jump, what it's going to do is going to use the address of where it's going to, right? Where it's jumping to. Your target address, it's going to put it into the register, which is register 7. And it's using register 7 specifically for these things. You're going to see when you look at your simulator, you might see some traps with the value. We'll talk about that later. We will see, register 7 regularly being used in those cases where we halt, we jump, or we branch. So it does allow any kind of target address. However, it's whatever the destination or the target is, it's going to put it into the base. So it's going to go to the location of the target address based on the base here, which are these 3 bits. Okay. So if I'm using BR only can access 256 on the positive, and then on the negative, on the decrement, it's 255 location before the instructions. So the rule is anything that is too far down, right, above 255, you should not use. You should always try to stick a little closer to where your instruction is. So if my jump line is the 5th line in my code, my fill addresses needs to be within 255 lines, or the addresses between. Okay, so it needs to be within the scope. So for the diagram level in the register, it's going to put the base, and it's going to use that base to load it to the program counter. That's how it's going to be able to navigate from the top to the bottom of your program or other area of your program, because it's associating the address of where it's going to. It's going to bring that to the program counter, and that's how it's able to go to that section. Okay, so it's loading the PC with the content of the register, which is specified for where it's going, where it's jumping to. And so this is also using a full address space, 16 bits, right? Unlike you've seen earlier with data movement, some of them only use half, which is 8 bits. Some of them only use 6 bits, as it's dedicating other bits for other things. In this case, it's going to use the entire 16 bits, full address space. It has no limitation. where the next instruction to be executed must reside. So at the C and C++ level, we don't use goto that much anymore. In the past, if you ever seen program in C or C++, sometime I do come across some older developer that they use goto. You can actually send your program from one section to another using goto. It's not a common practice these days because sometimes it can create a lot of problems in the program where you force it to go to a certain area where it should be executing some of the other processes before. So think of that as almost at the higher level how it would be equivalent on the low level. So it has no limitation. You can send it from one to the next and the next and the next and so on. Okay. We will have a lab that has jump. So let me see. Let me cover a little bit more and then we'll go through number 3. Actually, let's do number 3 and then we'll proceed. Okay, so for number 3, we are going to write instructions based on the criteria that's noted for each. For A, it tells you to load data from label count 1 to register 1 and explain whether we're using LD or LDI. And I put down 2. You don't have to put down both, but I want to put down 2 so you can see the difference. Now in the instruction itself, for the first one, for 3A, is we are going to do a direct load to register 1 from count 1 label. So you're going to do LDR, or I'm sorry, LD R1 and then count 1. So we have the label and the register. And we simply load count 1 to register 1. And then for the LDI, we are again loading count 1 to the register 1. Achieve the same thing. The LDI is going to be the indirect load. And when you do this, right, what you're doing is you're using memory address to point to another memory address that would load to register 1 for reading, to read data. Now, when you do a direct load on this, right, the reason for this, it's the same, but we are going to use PC counter, PC relative mode to locate address of label through the register. So as PC is tracking the program, it's gonna take the address of count 1 where we fill it. You see I fill it at 3102 here, right? It's gonna add it with the PC. So it's gonna put it in the PC, it's gonna put it in the MAR, and it's gonna use the MAR to be able to access, right? Or use the register to be able to access the whatever the content initialized with the count 1. Okay. For B, we're going to store data to register 2 from label HW. We've seen this at the beginning of our class. right? Secondly, explain why you would use ST and STI instruction. Now, truly, it's really a preference with developer, right? But if you think about the low level, why would you use direct load? Well, ultimately, if you can skip, right, one memory address location, but ultimately when you using a relative PC mode, it's another memory location. So it's about the same ultimately. The store data here, what we're going to do is we're going to do an ST register to, we're going to store it to HW. So the content of register to, we're going to put it to the location of HW. So in the back, right, before it does that, when it does the store, it's going to take whatever that's in R2, usually addresses, and it's going to add it to the PC, add it to the MAR, transfer it to MDR, and then be able to access this. About 4 steps. For the STI, there's an additional step because it first needs to store it to, it's going to take the address of register to, okay, to be able to put it into the MAR, transfer it to the MDR, add it with the program counter, get that address, be able to put that address into the MAR, and then it's going to be able to locate the HW. Okay. So at the higher level, we can see that this is a way to point to the location of the label with the R2 content, which is address to address. Any question? And then for C, when we talk about, let me bring this up real quick, sorry. When we talk about LEA, load effective address to register 0 from the label ADR, what must you specify in ADR before issuing the instruction in LC-3? Because it's bypassing memory, it's not using memory, you have to specify the content or your data. So you have to initialize data when you're using LEA. No exception. So in my note here, or for the answer, I put LEA R0 ADR. This is what the question calls for. It actually moves the data from the label to the register 0, right? It's not putting it to another address, pointing it to another address, or bringing it into a certain memory region or location, and so on. So LEA, you have to specify data or the content in ADR by declaring that label. So this is what we see with string is it's actually the content at that location, and you must specify it for LEA. Any question? So for D, we simply jump to a register. We're going to do jump R4. We're going to go to register 4 location, assuming that prior to this instruction, we might have load R4 with something, or we did something with register 4, right? So we can send it to a location. So it's going to base it on the address or whatever that's inside of R4. Usually just address. Remember what I said, software level, it's just how we're able to read and write with memory. And at the low level, you see this. And then when you look at the simulator for E, when you execute the halt instruction at the end of your function or at the end of your program or a certain subprocess, basically you want to stop that particular process there. So it uses a trap vector. So on the simulator, it's going to tell you trap, and then next to it, there's a value, and it is a hexadecimal value. So when you use halt, that's going to be a trap hex 25. And there are different trap value associated with pseudo instructions. I think we saw some of this earlier, and we're going to revisit it again. So when you look at your simulator at the end after you ran your program, at that line, when you had the halt, once it executes it, it's going to show a trap. Okay. And trap use, again, register 7. So you have the ending register being used for some of the pseudo instructions and some of the control type of instructions. Okay, any question? All right, so here it talks about trap. This specifically is for system service call. You've seen this with input, output, halt, right? Get C. So this is a service routine. And this is why when we see it with the pseudo instruction, it's really system related. Basically, service routine is function for the system. Because when I issue the trap hex 23, it's going to wait for the keyboard input, right? It's going to wait for that signal. When I issue a trap hex 21, it's going to wait, it's going to generate, right? Or it's going to be able to generate a signal for the monitor to be able to transfer the data to display. And then for the halt, it's going to terminate. So it's going to send a termination signal. So at the end of your program, when you finish, if you're looking at the register 1, it's always going to show a -1 because what it has to do is has to subtract 1 where it moves. It's going to have to give back that memory space to, right, whatever that's going to be used later on, another program. So when it does that, it's going to terminate the signal. And once that termination signal is generated, the register 1 is going to have a -1. It has to issue the -1 for the program counter, where it's going to decrease 1. So it's going to subtract 1 of your full address space for the end of your program for the next program to use. Okay. So when they talk about like when you do return 0 and all of that, right? All of this, you basically have a system service call at the end. And to be able to give up the space, clear out the stack, all of that happening with the compiler. So that way the resource becomes available for other things. It gives back to the OS. So for the trap, the opcode trap, you're going to see that it's going to have 4 bits of 1s in the front like this. So that's how it knows it's a trap. And then for between, you're going to have 4 bits of 0. And then whatever the vector size, right, whether it's 25, 21, 20, that's going to take up from bit 7 to 0, which is 8 bits. Okay. And at the micro instructions right here, so you have the 0 extended here following the opcode. And then it's going to use the MAR, transfer the content to the MDR, just like a lot of the other instructions. Your register 7 is loaded into your program counter. So in this case, what we would see is that there is a return or the return for the service call. We also can use RET, right? But with the trap, what will happen is when you're using a trap like this, it's going to use the return no matter what, return of the service call. Okay. And then after the MAR to the MDR is going to go put the content into the PC. And that's how it's going to generate the trap. Computing with whatever the vector that you specify based on your pseudo instruction. So if I want to do an out, it's going to use a hex 21, which is different than a put. Okay. Out only gives you one character on screen or on your console versus put more than one character. It's a string. So it's pointed to a string that is loaded LEA to register 0. So normally you use puts with string and out for one character. Question? All right. So now let's kind of go through like this, right? Before the end of this class, I really want you to know how to write instruction well, so that way you can do your project. You will be able to understand and apply concept in this class, because assembly is not easy. Sometimes it can be confusing. So we're going to keep practicing until we get it, right? Some of you already got it. Some of you are already like, oh, that's really easy, right? But sometimes this is like learning a new language, so it's just taking time to process. All right, so for number 4, we're going to go through each one and we're going to write it out in LC-3. For A, I'm going to initialize register 1 with a 0. This is easy. We know that this is a clear. So we are going to do an AND register 1, which is the destination here. And we're going to do it with itself. So register 1 with a 0. So anytime you AND with a 0, you're going to have 0 as output. So we clear register 1 and register 1 has 0. So as you go through this, if you can do it without looking at what I have or notes, then you're good, right? You'll be able to put together a simple program. All right, for B, we are going to initialize register 2 with a decimal 3. So that's easy. We are going to take 3, which is the decimal. We're going to add it with register 2 and put it back onto register 2. So here I'm going to use operational instruction. We're going to add register 2 with the decimal 3 and then store the output on register 2. So assuming that register 2 has nothing before, then we have register 2 has decimal 3, which is an immediate value. Now I want to copy for C. It tells me, and this is kind of like reassignment in higher level. So I wanted to take the content of 2 and make it the same as the content of 3. Okay. So I can do it 2 ways. Okay. As the problem read, if we read it left to right, it should be R2, R3 here. Okay. But if you read it the other way around, it's not wrong. It's just going to be exactly the same. So if I have register 2 has 3, by the time I finish this code, right, register 3 also has a decimal 3. So it doesn't matter which your destination is, the content is exactly the same, right? So if I have like this or like this, it's the same because they're both has the same value. So we want to copy the content here, make it all the same for both. So we're going to do add register 3, which is here, right? Originally has 0 with 0, and then put it on register 2. Now, if we do this, register 2 at this point is going to be R0, or be 0. I'm going to show you the difference right now. Okay. But if we make it like this, okay, so your R3 is equal to, right, decimal 3 plus decimal 0. Whereas the other one right above here, what you're going to have is you're going to have R2 is your register 3, which is nada, right? We don't have anything yet. R3 plus a 0. And then so what it's going to do is going to take the content of this, and R2 already have a 3. So assuming that if I have a 0 here plus a 0 and then add it on to the 3, I'm still going to get a 3 plus R2 content, okay, which is a 3 ultimately. Any question? So you do have the same output at the end, but if you're looking at the order how it is, right? On the inside, it is slightly different, but you are achieving the same thing there. Okay, so this or this. Then when you have 9 is going to initialize at R4, we simply add 9 to register 4, assuming that it doesn't have anything yet, and then put it on register 4. So register 4 half decimal 9. Okay, any question? All right, so now we're going to take register 2, add it with register 4, and put it back on register 2. So that's easy. We're going to take register 2, add it with register 4, and put the result in register 2. So add R2, R2, R4. And so when we look at that, it is your R2 has 3, right? R4 has 9. And that is going to be decimal 12. Or if you treat it as hex, because the simulator will show you the hex value, you just find the 12 equivalent. So A is 10, 11 is B, and 12 is C. So they are hex C. Then on the next step for F, we're going to take register 3, add it with register 4, and store the result in register 3. So we're going to take register 3, add it with register 4, and store the result in register 3. Okay, so add R3, R3, R4. And so if we look at what could be the value, right? So your register 3, remember that we copy it earlier, and it is also 3. So 3, register 4, we had it as 9. So 9 decimal 3 plus decimal 9 is decimal 12, or it also is a hex C. I'm going to put the lowercase because I don't want you to think that it is an instruction. Then for the next part of the code, we're going to say if register 3 is decimal 12, go to R2. Assuming that we would have a label tied to R2. So I am going to, because the previous line here, right? The previous line here, it's going to check what's in R3. Okay. What I can do is I can subtract 12 from R3. And if it is 0, then I can send it. I can make it jump, or I can do a branch with that, or I can, in this case, it says go to register 2, assuming that it ties to a label. So what I note here is that you need to check for 12 by subtracting 12. You can branch for positive or 0. Actually, I want to branch for 0 in this case. And so let me fix this real quick, okay? So let's say that we last left it with this, right? We can add R3. Let's do not. And then we're going to, sorry, I had it backwards. So let's do an add R5 with a hex C, because I don't want to add multiple steps. So we're going to do a not R5, and then we're going to add R5 with a with the 1. So as you can see that I'm getting ready, what I'm getting ready here is I'm getting ready to subtract 12. Okay. You can make it decimal 12, or I just use the hex. See, the same. So at this point, your register 5 stores a negative XC or F, right? The 2's complement of hex C. And then what I want to do is I want to add this to register 3 and put it back on register 3. So register 3 is equal to 12 minus 12, or hex C minus hex C. And I want to check to see if it's 0. Let's name this something else. Let's say 0. And then, all right, so once I branch it there, I'm going to define it, right? And so because if register 3 is decimal 12 or hex C, I'm going to send it to register 2, like go to R2. We can branch to 0, and then we simply are going to we can branch to 0, and then we can load it to the register.
Supposed to jump.
Yeah, if you, or actually I'm trying to not do a jump you can jump, but I'm trying to do a label to a register because it's better because it says if this, right? So we can check for the true condition because jump doesn't, oh yeah, so yeah, we can do that. I see what you're saying. JMPR2, easy. Is that clear? So once I subtract the 12, I know that register 3 has a 12, right? Because previously up here, right, we said that we want to check. So at the end of our code for F, we know that register 3 has a 12. And if I subtract 12 from it, I would get 0. So it checked true for this. So when I subtract register 3 here as 0. And then I send it to 0. And at 0 section, I can jump it to register 2 because it met the condition that register 3 has a 12. Then go to register 2. But I was thinking another way, instead of doing a jump with the register 2 here, is to tie, because ultimately you have to tie the register 2 to an actual address so you can check the value, right?
Yeah.
So I was gonna do the 0 section, I was gonna store it to, or I can load register 2 to another label and then fill it with an address.
Yeah, it would be something
So
we didn't previously, right? It's
right.
yeah.
And that's more realistic because when you jump here, it's not done, right? We
Yeah, it's
can't,
not accurate. We're not gonna know what's
right,
in there realistically.
right, that's correct. Because when you jump here, your program still continues. You have to finish your program because what's going to happen here, you can't check register 2. So you have to store, right? ST, or we can do an ST register 2 to a label, let's say a val. And then you're going to do, later on, you're going to do a val, and then you're going to do a dot fill. And we can tie it to an address, like let's say 3120, like this. So I was gonna try to skip the jump, but yeah, the question itself, it is right. We can go here, but you don't have to jump to register 2. You can actually, in the 0 section, because you branch here, for 0, you go here and then you can just store it.
Yeah, because we already know it's true, right? Because we branched
Yeah.
off.
And I don't like using jump so much because you cannot force it to be in a criteria. Like there's no condition to be met. So we have to use it here. If we use it earlier here, right, we won't be able to check if that's true. So I have to branch and then jump. So I can, yeah, so this is optional actually. You can't just go store directly to val and then fill it because you don't have to jump to it. So when you jump here, what's going to happen is your register 7 is going to have the address of register 2. And then at that point, it's going to return that address value. So if we still going to use that address value and we're going to store it back into register 2 and then tie it to another address. So I think, in my opinion, that's just an extra step that you can probably skip because it's involved 2 additional processes. So you can just like not have to jump to store it from register 2. And assuming that register 2, have something from up here, right? We store the value from register 2. Okay, so yeah, realistically, we have to go to a physical address to simulate and check the value. But that's how you write it.
Would we put a halt at the end of BR's?
Yeah. Yeah. Ideally, because halt's gonna return, and if it has nothing in the PC, right there, if there's no other line to fill, then it's gonna return, it resources back. So it's gonna hit the R7 is not gonna have the next code address, the next line address. So it's going to give the resource back to the computer or the operating system. Any question? So my suggestion is you have to really think about the step before you branch. Like, what do I check for? In this case, we're checking for 12, so we subtract it. And if you want to check for positive, you can use a higher value. Like I can add a positive number, but it's really hard to check with the positive because how do you know it's exactly 12 if you're going to check for positive, right? Easier if we just subtract 12 from it. We know it's exactly 12 if we subtract 12, well, we can check for 0. So if I take 12 minus 12, I know that my original value, the content in register 3 was 12, and I can branch for 0. But if I want to check for positive, then I just initialize my other register with a different value and then subtract it. Okay. So there are several ways to really solve this problem. Is it completely wrong? No, sometimes it's a little bit more lengthy in assembly if you go around and about of checking things. But you have to think about like, do I need this step? How can I, if there are additional unnecessary processes, then you don't need it. Okay, if I can store directly and just do that instead of jump and then store. Okay, any question? All right. We have a lot of time. This is actually not too long today, but so for the branch, right? Branching instruction, we touched a little bit of this on this when we talked about it in the lab last time. You saw this for a while now in 2 labs. So branch, you can check for negative, 0, or positive. Sometime we would do like multiple, right? 2. Usually if we do less than or equal to, greater than or equal to, this is when you branch for with multiple conditions. So this is where you can have 1 or more condition codes. And in the addressing, it's going to go to the target address. You normally branch to a label like what you've seen in my assignment here, right? I branch to the label 0. And then after that, I would fill the body of the label. So whatever that it's supposed to do, you can tab it or you can use the below line. That's fine. So it's going to use the target address, which is my label. Okay. So at this point, what if I have a bunch of code in between here, between the branch and my label? You've seen this in the last lab. So it's going to use the address of that instruction for or the label, right? The instruction label there, and then be able to put it into the program counter. That's what it's going to use for the target. So when it sends it, how does it know where it is? It's the address of 0. Okay. All right. So that's what it really trying to convey right there. So as your program move along, your program counter is already incrementing because it needs to prepare to, it has to fetch, decode, right? And then execute and then so on. So what you have is it's already has the incremented information for the address. And so again, right, like the rule for assembly or LC3, we should know that it has to be within this range. 256 words or memory location, because each word is 16-bit of the BR instruction. You don't want it to be too far down. In the case that it is very lengthy in the program, you should think about the mechanism on how you're going to move from one area to the next area and so on. Right? I've seen programs for projects that's come in with 1,000 lines, right? And in that case, sometimes if you put it too farther down, it would not be able to reach. So we have to think about like how it's able to access it within 256 or less. Okay. Okay, so the example here, it shows you how you can compute sum of 12 integers. We see this in C++ or Java, right? You can randomly generate 12 integers, and then you just use a loop to add them. Okay, like, you know, as it generates, it puts it into, I don't know, a dynamic array, and in Python we would use a list, so that way it just increase. So we can have it for loop to randomly generate, and then for loop to compute, or we can nest it all in, and that will be just one function, and we use that function call. So it's gonna loop to generate, and as it loops, it's gonna add. That's called running sum. So in assembly, you're gonna see that it's a little bit more steps. Okay. And then, so we'll talk about looping and everything else. Okay. So the reason why that they're using a 12 here, right? Because you have to indicate, right, the max number of the loops that you're gonna go through. So if I'm generating 12 integers, I'm gonna start with the first integer, and then I'm gonna go all the way up. So as it goes, it's gonna increment. So you're gonna do 1, 2, 3, 4, 5, and so on. When it reaches 12, it's gonna stop the loop. So you have to introduce the maximum count into a register and the minimum count into a register to start a for loop, right? Because in C++, you see this, where you start, where you stop, and how you update. That's 3 parts in a for loop. So you have to have a start, a stop, and then the increment is the +1. This is what you see here. And as it goes, you got to subtract 1 from the 12 too to count down. So we'll work on the loops in our labs, and you will see. Okay. So I give you a little bit of example there. All right. Any question? That's just garbage note that I added a while back, but yeah. So when you finish, this is a short assignment submitted into Canvas. I'm going to go ahead and start recording.